Let's look at a particular algorithm which is known as a pioneering algorithm in identifying the frequent item sets which are occurring in a transaction database. This is known as Apriori algorithm. Apriori algorithm is basically a way by which we use a property called frequent item set is also a frequent item set but of lesser value of k. So if you have 4 set, show that the subset of it which has 3 items is also a candidate for the same. So that is why we need to understand that all of this basically enabling you to create a very efficient algorithm to generate the frequent item sets in a large reasonable minimum to run an upright. Let's start with a large set of those minimum. Then use relative of satisfies of size k with minimum support. Then to expand that, we may want to increase that with more items from the remaining. So what we will do that is we will only do that when we have candidates which have minimum support. In the sense, when we have an existing set of size L with K, then if you look at additional can plus 1, do not go below the minimum support. Let's show that with an example. Let's see this example. This is very interesting. Let's take this particular data item, which is basically talking about minimum support let's take the minimum support as 50%. Here we have 4 items. When we do a scan, we found that if you take the item set with of size 1 and we see the candidate 4, there's only 1, whereas others have 2 and 3, so we remove the candidate with less than the minimum support. Now we have an item set of size 1 and candidates are 1, 2, 3 and 5. Then we start to look at expanding that to the next set by adding one more element to this current set. We find that the only elements which have to be dropped are the combinations 1, 2 and 1, 5 because they're below the minimum support. Then we go and see that from 1, 3, 1, 2, 3, 2, 5, 3, 5, which have more than the minimum support, we want to expand with another item in the two-way set. We create a 3-item set. We find that there's only 1 item set which is of size 3 and is supporting, that is the item set 2, 3, 5. See, this is a very intuitive algorithm for expanding by starting with item set size 1, then expanding with adding it to additional items and removing at each point those candidates which do not follow the minimum or do not allow for the minimum support. So what is So I hope you can see the screen now. So see the steps here. What we're seeing is at each step, we are basically trying to remove those elements or the item sets which do not satisfy the condition of the minimum support. So that is what is going to basically define the contour of what the final frequent item set which is satisfying your minimum what you call support condition. So that is the first stage of your algorithm. So what did we do here? We took a step-by-step approach, started with item sets of size 1, removed those which did not satisfy minimum support level, then went on to expand the eligible candidate item sets of size 1 with addition of one more item, those which do not satisfy those with support of 1, which is less than the minimum support that's required. Then now we have started looking at expanding that to 3. There we had eliminated all the other combinations, but we have only one combination, which is 2, 3, 5. So this gives you an intuitive idea of the first phase of the algorithm, which is about identifying the item sets with minimum support. Now let us go to the next phase, which is how do you generate candidates to determine your rules which are going to output as the associations which are present in the data. There it's again simple. What we do is we generating and pruning based on confidence. We start with basically the frequent item sets of size I. Then for each item set in the I-1 size, we look at if any of the two elements in there are equal, we try to remove them and we try to create optimal incremental item set to the existing item set of size I-1. Basically what we're saying is if any two elements of the smaller size are equal and if they're anyway present in the smaller subset, there is no point in adding these extra elements and we add only the incremental subset to the relation which you capture. So ultimately when we generate this rule, we are only left with an item set, but then we also want to consider within the item set that is discovered, what is the set of rules that you want to output as the what you call one satisfying your confidence. That is where you start looking at permutations of all the item sets that you output from your previous stage. The item set I1, I2, I5. Here the kind of rules you can create is like I1 and I2 implies I5, I1 and I5 implies I2, I2 and I5 implies I1, I1 implies I2 and I5, like that. You can have systems. But then what allows you to discover which one of these is basically going to be the rule you're going to output is going to be derived by if the support is greater than min conf, only then you'll go and output the particular rule like I minus C implies C. Let's look at this example where we're talking about a set of we find that for combinations here like I1 and I2 implies I5, we have support of 50%. In some case, support of 33%. In some cases, 29%. This is coming by looking at the frequency of the left-hand side items and dividing them by the set of item sets where both and left-hand side are present. So once we do that, we are able to filter to the set of items which are basically going to support what is the minimum confidence that you have in this. So this is a fairly intuitive algorithm. There are several variations to this basic algorithm of finding association rules which have been discovered in context of databases. Key thing mentioned here is typically when of the confidence is supposed to be very high, and support is usually not that high because trying to find rare which are